This is a supplement to the last lecture. This supplement is specific to Physics AB. In the last lecture, I calculated the work done by the spring force over a closed path. And what you saw me do was an integral. Now, of course, Physics AB is an algebra-based course. It's not a calculus-based course. So then therefore, what I want to do is I want to repeat that calculation, but in this case, I want to do it for you algebraically. I want to calculate the work done by the spring force over a closed path. The closed path, however, is going to be identical to what I described in the previous film. We're going to start here at position A at equilibrium, and then we're initially going to stretch out the spring here to position B, and then in a few moments we'll go backwards from B to A. What we'll do is algebraically calculate the work done by the spring force as we first of all go from A to B, and then secondly from B to A. Okay, recall how this is done from earlier in the unit. We have to calculate the work done by the spring force by using the average value of the spring force. Right here at position A, because we're at equilibrium position, the spring force here has a value of 0. However, over here at position B, when we displace the spring like so to the right-hand side of my diagram, right here the magnitude of the spring force is equal to K times X. The average of the two, 0, and Kx is Kx over 2. That's the value that we use when calculating the work done by the spring force. Okay, so the work done by the spring force as we go from A to B is now going to be the average value of the spring force, Kx over 2, times the displacement vector x, and then multiply by the cosine of 180 degrees. There's a 180 degree angle between our displacement vector here to the right-hand side and the spring force to the left-hand side. Cosine of 180 degrees is equal to -1. So then therefore we end up with the same value as we did in the calculus version of the calculation, -1/2 kx squared, but now we do so here algebraically. But then we still have to go backwards. We still have to go backwards from B to A, so then therefore let me just redraw the diagram on the lower board. Okay, so now what we're going to do is we're going to start here at position B. So here's equilibrium. This is position B, but now we're going to go in this direction to the left-hand side of my diagram, this displacement x. In this case, the angle between the displacement vector and the spring force vector, which is still back towards equilibrium, is not 180 degrees. Instead, it's 0 degrees. Okay, let me go ahead and finish off the diagram here by also drawing position A once again. So here's equilibrium, and then here we are back at position A. Once again, in order to calculate the work done by the spring force, we use the average value of the spring force. Right here at position B, when we're initially stretching out the spring, the magnitude of the spring force is equal to K times X. However, over here at position A, we're at the equilibrium position, the value of the spring force there is 0. Therefore, the average of the two is once again Kx over 2. So now, the work done by the spring force is equal to the average value of the spring force, Kx over 2, multiplied by the displacement vector x, and then multiplied by, in this case, the cosine of 0 degrees. There's a 0 degree angle between the spring force and the displacement vector. Cosine of 0 is +1, and then therefore we end up with +1/2 kx squared, just like we did in the calculus version that you saw in the earlier film. At this point, however, going forwards, the remainder of that film would be identical for Physics AB as it was for the other classes. You add together the two values here and here to get the work done over the closed path. It's equal to 0. Therefore, there is potential energy associated with the spring force. That then led us to our statement of spring potential energy and conservation of energy with the subsequent example that I performed in the previous film.